Hi everyone, today I wanna present the conference paper called Reinforcement Learning Based Mixed Signal IC Replacement for Fogging Effect Control. The authors of this conference paper are Mohammad Jafari, Mernaz Ahmadi, Jenshin Zhao, and also De Liang Zhang. I present this conference paper in ISQD 22. I'm as a speaker, I'm Mohammad Jafari. I'm studying Master of Electrical Engineering at Memorial University of Newfoundland, that is located in St. John's, Newfoundland, Canada. My studies focus on electron beam lithography challenges. I mean the scattering in electron beam lithography. So this is the outlook of my conference paper. In part 1, I talk about the overview of the fogging effect. In the part 2, I introduce our modeling. In part 3 is the main part of our presentation, that is the BSR Tree based reinforcement learning placement. In part 5, the experimental results are demonstrated, that is divided into 2 parts, the timing and also the performance comparison. And finally, I talk about the conclusion. So why we use the next generation lithography methods, or NGLs, and what is the NGLs? Based on the Moore's law, the number of transistors in a specific area of the chip will be doubled approximately every 2 years. So the transistor getting smaller and smaller, and we need the better resolution to create fabricate these semiconductor devices. The traditional lithography method, that is called photolithography, has 2 limitations. The resolution and also the graphy has 2 limitations. The resolution and also the mask cost. So we need to some new methods to be replaced with this traditional method to have a better resolution for the new technology nodes. So these methods called NGLs, and they are used in industry nowadays to get a better resolution and also save more money and energy in the semiconductor industry. Okay, one of the most popular NGLs is electron beam lithography. As you can see here in the picture, the electron beam lithography process has a gun that emitted the electrons, and also we have a control part that the blanking plate and deflectors are in this controller that control the electron beam and emit and expose the electrons to the specific point and area on the wafer to print a pattern on the wafer. So this method has some advantages. For example, the direct writing that doesn't use any mask for lithography, and also it has high resolution. I mean, the resolution of this method is down to a few nanometers, and also there is no light diffraction. But we have some challenges in this lithography method that is called electron scattering. So as you can see here, we have a primary electron beam that is emitted from the electron gun to the resist and also the substrate, but there is some scattering here. We have 3 kinds of scattering. The forward scattered electrons that are green or orange, and also we have the back scattered electrons that are purple, and also the scattered electron. The scattered electrons that are green arrays are cause the fogging effect. I mean, the back scattered electron hit the bottom of the lens and then rescattered to the resist and cause the fogging effect. So this effect lead to the critical dimension error. I mean, the gate length will be changed by this error, by this effect. So based on this, if the resist is positive or negative, the gate length will decrease or increase. So there is 2 main characteristics of the fogging effect. I mean, it has low intensity but high range. The range of the fogging effect up to 20 20 millimeters. So it can be really considerable in some specific conditions. So why we consider the fogging effect in mixed signal IC? As you can see here, based on some experiment that is done, when we have a large area of the patterns and large amount of the module and transistor, so in that part the fogging effect is considerable and noticeable. So we cannot consider the fogging effect just in analog part, because the source of the fogging effect in that part is low. But when we consider it as a part in the mixed signal, we have a digital part that there are a lot of module and transistor as a source of the fogging effect that lead to the considerable amount of the fogging effect on specific transistor in the analog part. And there is another point in the mixed signal ICs that we have some sensitive transistor that we want to protect from the fogging effect, because it causes some, for example, mismatch error in our circuits. For example, one of the parameter that can be changed is voltage threshold voltage of the transistor. That is depends on the gate length. So when we have a fogging effect, the gate length will be changed, so we have the variation, for example, in the voltage threshold. So we want to protect some sensitive devices from the fogging effect variation to minimize the difference of the change in those transistor in a sensitive pairs. So to study the fogging effect distribution of that, as you can see here, the energy distribution of the fogging effect is a Gaussian shape, and the formula of the energy of that is something like this, and the W is the range of the fogging effect, and X and Y is the coordinate of the target point that we want to calculate the fogging effect on that. But in our study we use a PointSpirit function model of our fogging effect that is can be shown by this formula that you can hear. The R is the distance from the target point from the primary electron beam, and also the lambda F is the range of the fogging effect. So as you can see here, we have a digital part and also we have the analog part here that we want to consider the fogging effect in this analog part. So we want to consider the fogging effect in this analog part. So we need to calculate the fogging effect in each point of the analog part if we want to minimize that. So we use if we want to use the traditional method, that is a convolution between the fogging effect, the PSF of the fogging effect, and also the density map of the pattern density of the of our chip. So this convolution is so time consuming, so we use another method that is accurate approximation for calculating the fogging effect. That is a fast Gauss transform. It called fast Gauss transform. That, as you can see here, it depends on the TI-SJ. The SJ is the source of the fogging effect. I mean each of these effect, and also the TI is the target point that we want to calculate the fogging effect on that, and delta is a constant that is considered, that can be defined by the user, and QJ is the weight of that source of the fogging effect that caused that source of the fogging effect, that in our study it can be considered as a pattern density of that source of the fogging effect. As I told before, we want to minimize the variation of the fogging effect between two transistors in a sensitive pair that we have in our analog part. So as you can see here, for example, we have a sensitive part. We have two transistors that is shown by blue squares, and also we have some other source of blue squares, and also we have some other source of the fogging effect that is shown by red, as you can see here. So we calculate the fogging effect in each of these two transistors, and then we calculate the difference between them to achieve the variation of the fogging effect in these two transistors in one symmetric in one sensitive pair. So our goal is minimize this variation of the fogging effect between these two transistors in sensitive pair. So we use the reinforcement learning for our placement. As you can see here, so there is some fundamental of the reinforcement learning. We have agent and the environment, and the agent gets some experience from the environment, get reward from the environment, and based on that reward take action and try to train itself based on that reward to take the best action to get a better rewards from the environment. So we have the agent here, that is the main part of our reinforcement learning, the actions. The environment, that is the word of our problem, that here is the chip, the chip placement, and the state is the different configuration of the environment, and the reward is the result of the action that the agent received from the environment. Okay, here we want to take advantage of a deep neural network for our placement method. When the reinforcement learning use a deep neural network is called DQN, and we use deep neural network as our agent. So when we use a deep neural network and train that to take the best action, so the agent take the action intelligently, so it can improve the performance of our agent to take the best action in a less time, in a shorter time. And also the main purpose of our agent is finding a optimal action value function that can predict the Q value on the output layer. We want to train our agent to find the optimal action value function that can predict the layer. And also we use the BSR tree as our environment in our placement. So as you can see here, we can have the BSR tree for a placement that we have, and also we have the packing that can transfer the B tree to the placement. By the packing we can calculate the coordinate of our module based on the B tree that we have. So when we have a B tree, we can have a corresponding placement of that by the packing, and also when we have the placement, we can have a BSR tree of that placement. Here you can see our proposed reinforcement learning based placement method. We have the agent, that is a deep neural network that intelligently take actions, and also we have the environment, that is the BSR tree that represents the chip placement. And also when the agent take a state from the environment, and based on that state, and also the trained deep neural network can take actions, and the environment take when the environment receive the action, based on that action calculate the reward and send the reward to the agent. And this iteration will goes to train the agent to take the best actions. So here you can see our reinforcement learning agent, that is a deep Q network. Our neural network has two convolutional layer and also the max pooling layers to downsample data to make to remove the unnecessary data and speed up our training. And also we have the output layer. The nodes of output layer, it depends on the actions. We have 4 actions here. I mean the swap, the 2 nodes can swap, and also the nodes can move, and also the nodes can rotate, and also no action. So we have 4 action for each modules, and also we have for example the 8th number of modules. For each module we have 4 action, so totally 4 times 8, we have 32 nodes on the output layer. So the output layer, it depends on the action and also the number of modules. I talk about the action, and also about the training. We want to achieve the optimal Q value. The optimal Q value is calculated based on the reward and also the Q value in the next states. And we have here the discount factor. The lambda is a discount factor. And also we have the loss function to train the agent. That is the mean squared error of the Q value that we have on the output, and also the optimal Q value. So as I told before, our reinforcement learning environment is a BSR tree that shows the placement of our chip. The states are different configuration of the BSR tree, and also we need to calculate the fogging effect. One of the D is calculating the reward and sending that to the agent. So we calculate the reward based on the cost function. In our cost function, we have the area, the wire length, and also the fogging effect variation between transistor in a sensitive pairs. And also each of them has their weight. So as you can see, alpha, beta, and also the lambda I is a different weight for area, wire length, and also the fogging effect variation. So based on this cost function, we calculate the reward. We have the user defined threshold cost that in our study is 700. So based on the comparison between the cost function that we calculate by this formula and also the threshold cost, we calculate the reward and send it to the agent. So here is our experimental result in two sections. The first one is the performance and the second one is for the timing. It is for the 2-stage op-amp. As you can see here, our method in area and also the violence is slightly worse than the simulated annealing method, but in minimizing the fogging effect variation, our method is 92% has 92% minimization of the fogging effect. That is much better than the simulated annealing method. So because of that, in our method, the DC gain of the 2-stage op-amp is 52 rather than 44.58 in simulated annealing method. So as you can see here, the performance of the our method is much better than the simulated annealing. And also for the timing, our timing is much better than the simulated annealing. However, the simulated doesn't have the training time, but generally our method is 4.4 times faster than the simulated annealing. So why our method is faster than the simulated annealing? That is because of the number of state. The number of state in our method is 1.4 times 10 in power of 10, that calculated by this formula. That is different configuration of the BSR tree, but the number of state in simulated annealing that is calculated is 2.5 times 10 in power of 11. That's based on the calculation. They have simulated annealing has 18 times more state, and that is the reason that our method is faster. So for conclusion, our method has better performance in minimizing the fogging effect, and also while it is faster, and also it uses DQN and also BSR Tree that can lead to take action intelligently and also in simpler environment. Thank you very much for your attention. If you have any question, you can send me email by this email address. Thank you very much for watching.